Welcome to Mastering Solutions. Let's start this question by making a list of everything we're given in the problem. We know that L in this case is 1 meter, the screen behind the diffraction grating. The wavelength of light, they say, the lambda, is 600 nanometers. And we're needing to find what D is, or how many lines per millimeter the grating has. And that is going to be the width over slits. And in this case, they said that they want it in 1 millimeter. How many slits does it have? So in order to do that, what we'll utilize is two equations, and we've used these in the past few problems, so they'll feel familiar. Y is equal to L times the tangent of theta. We're going to use that to find what theta is, and then we'll plug that into the second equation. Sine of theta is equal to m lambda over d. We know that this right here, this peak is the central max, and off to either side, they're equally spaced. So that is m is 1, and these ones will be m is 2, m is 2. So we can use this delta y from the central max out to a bright fringe for our y value. So we can add that to the list here. We'll say m is 1 for what we're going to do. You could use m is 2 and you would add these two values together. But for this y, we'll have 43.6 times 10 to the negative 2 meters. In this case, it is a little easier to just move the decimal place 2, which is 0.436 meters. So we need to isolate theta in this first. And so we have y is equal to L tangent of theta. So we'll divide both sides by L and then take the inverse tangent. And so that will give us inverse tangent of y over L is equal to theta. So we have all of these values now. So we can say inverse tangent of y, which we said was 0.436 meters, divided by L, which we said is 1 meter. So our angle is going to be inverse tangent of 0.436, and it's divided by 1, so we don't need to enter that. Make sure your calculator's in degree mode for this, otherwise we'll get radians. We have 23.557. That is an intermediate answer, so that's the degrees for our diffraction grating here. Now we need to take this and we need to find out what D is. So we need to rearrange this equation here. So we have sine of theta is equal to m lambda over d. What we'll do is we'll first multiply d over onto both sides. So we have d sine of theta is equal to m lambda. And now we'll divide by sine theta. So finally, we have d is equal to m times lambda divided by sine of the angle. Let me scroll down and give us some more room. So let's plug in all of our information here. We know m is 1. The lambda is 600 nanometers. And then all of that's divided by the sine of the angle, which we found was 23.557 degrees. So we have 600 times 10 to the negative 9 divided by sine of 23.557. So we have 1, 2, 3, 4, 5, 6. So we'll say 1.501. So the answer is 1.501 times 10 to the negative 6 meters. Now that's just an intermediate answer. That's not how many lines per millimeter we have. This is if you take 1 millimeter and divided by whatever this is, gives us the 1.501 microns. So we need to do some algebra here. First, we'll multiply both sides by whatever this slit spacing is, and then we'll divide over this. So we need to take 1 millimeter divided by what we just found, 1.501 times 10 to the negative 6 meters. And that will give us how many lines there are per millimeter. So we have 1 times 10 to the negative 3 divided by our previous answer. And that gives us 666 so we'll round to 666. So for this question, there are 666 lines per millimeter in this diffraction grating.